BioSolveIT, I'll try to give an overview of what currently is in our Armory to tackle the fragment-based chemical spaces that we explore nowadays with very efficient methods. And I was, just as you, Alex, blown away by what Xavi was talking about using spacemacs, for example. So how can we go beyond the enumeratable? That's my topic of today. The thing with going beyond enumeration is, or the thing with enumeration above all, is that we have limited compute power. And to exemplify this thing, I would like to make a little experiment and let the computer count while I speak. So here's a little Unix command that gracefully on the Mac will work just as well. So I can let it count. I can say sequence minus format this out with no floating point digits and count from 1 to 5. The computer is fast. I can count from 1 to 100. The computer is still very fast. To 1,000, to 10,000, even super fast. So why not let we count the computer up to a zeta range of numbers. So a zeta means 10 to the 21st. So while this now kicks off, I hit return now. The computer can keep on counting. I go back to the talk and we'll see at the end how far the computer has reached. If you really want to blow the budget, so if you have spare money, you could think about investing it in enumerating beyond where this thing turns red here, for example. At the beginning here, this still, and we will likely see this when the enumeration on the computer and the terminal window has finished, but 10 to the 8th, 9th or so, we can still rest comparably cold. Although still there, RAM requirements or CPU, GPU requirements can go pretty much high up in the numbers. I took these figures from the NIH symposium that was running on ultra-large databases. Down here you see the references. And gracefully and thankfully Wendy and more wrote this all up. If you Google for this, you will get a bunch of references, and many presentations are still actually available on the Cactus.gov website here from the NIH. So these figures are pretty impressive. 2,900 GPUs to convert smiles into 3D format, or to do a docking with 10 to the 10 compounds. People request roughly $250,000 for that. Superposing, storage, simple storage of molecular data can take up to 100 petabytes hard disk space that you can purchase from Google for 10 to the 11 sized spaces, and so on and so forth. So definitely this area here is hot in terms of energy consumption, time consumption, CPU consumption, and it's not exactly green chemistry of the future if you go beyond. That said, we see that chemical space sizes are definitely surging. So it was actually Alex who prepared this figure originally for us to use in presentations and to exemplify things. So down here, we have the size of the chemical spaces described, 10 to the 5th up to the 10 to the 26th. So these are the ones that have been published, that people talked about. There are a few more ones up here, corporate ones, that cannot yet be talked about. But if we take a look at all this here, we see that there are the collections that we all know. E-molecules plus, Aldrich, InStock, MQ, the Wuxi Virtual, PubChem. What's definitely obvious as well is when I again denote the area from small to up to roughly 10 to the 12th as still enumeratable, then up here, this is definitely no longer possible with the compute resources at hand currently. So we need different algorithms to tackle this area of chemical space sizes. What comes to remedy is the nature of chemistry. The nature of chemistry sometimes is A plus B equals C, but often it's more complicated than this, and we have A plus B plus C, a bifunctional B can happen to close a ring. But these can essentially be described in the computer as functionalized residues. For this azide residue here could be exemplified in the slide with a gray Lego block. And then what we need to do is record and store and make computer readable the compatibility between those Lego brick colors, for example. In that do something like this molecule and this molecule and this molecule will react to something. And this molecule and this molecule and this molecule will do the same. But there could certainly be all those cross reactions, which means that instead of simply counting 2 plus 2 plus 2, we have a combinatorial explosion that we can take care of if we have the proper algorithms that accompany this. And indeed, this is the case. The original thinking of all this is many years ago already, emerged many years ago. But the core of it all is the so-called compatibility matrix. So in there we encode that an amine can react with a carboxylic acid to form an amide, for example. The ubiquitous example that is always cited when it comes to such approaches here. So what we need to do is we need to input chemical know-how, for example, from Muji, Enamine, Otapa, but also your own in-house molecules and reactions can be taken, and people pull out information from publications just as well. And on the other hand side, we need the building blocks. These could be the purchasable ones, also in-house ones, things that AI methods come up with. And if you encode all these things and you have a pre-processing machinery, then you can create a chemical space that has this combinatorial character stored in and can reach zillions of molecules, for example, 10 to the 21st. I would like to give you a broad overview, as mentioned before, on the methods that are currently available now. But that said, it comes in very handy that on May 9th, so only a few days ago, there was a very special issue from the Journal of Chemical Information and Modeling here, namely this one, with a very striking graphic on the title cover here that shows these giant spaces here, but also the earthed ones, the grounded ones, with very high likelihood of accessibility and purchasability. For example, again, the ones that we just mentioned, but also the zinc 20 is in there, PubChem compounds, SAVI, NCI SAVI 2020 compounds in there. And I would like to point your attention to Wendy War's a grant review that she wrote up with colleagues. That's also published in here. So volume 62, pages 2021 and continued. So take a look at this. It's really brilliantly written and a great overview of things. So the Armory of chemical space exploration today, I put this on a honeycomb display here, and I will go through each of these very briefly to give you an overview. What we have currently available is beyond the 2D or coordinate-less methods is the 3D methods. Let's start with docking. So last year when we had our drug space symposium, I was showing you this slide. So we were presenting a full chemical space docking in the sense of including the chemical compatibility matrix in here. That means given a space with a bunch of molecules, many is a bunch here. In that case, we can dock all building blocks that contribute of this and run through this docking procedure with the building blocks, doing anchor and grow strategies, using the compatibility, do various sorts of filtering, sort things out, have clever clash filtering, etc., and then come up with synthetically accessible hits by the definition of the workflow. Today, in this year's Drug Space Symposium, we will detail this with an application example that will be given later on. I call this now agnostic full chemical space docking in the sense of that any one member of this chemical space may be a hit, may emerge as a hit in the end. And please go and hear Paul from Genentech, Paul Barosa, speak tomorrow at 6:30 p.m. UK time, 7:30 Central European Summer Time, or 1:20 p.m. Boston time. And I'm sure that this will be an exciting talk to listen to. Today, I would like to show you 2 slides on growing into a chemical space from a seed fragment that has been crystallized in a pocket. So instead of docking every building block into here, we could just as well profit from the situation that we have an X-ray structure with a bound fragment in here. So we would jump straight from the X-ray right into this position here. Our anchor has already been found experimentally, and we then just grow. Here's an example, and we are currently writing all this story up with Janis Müller being the first author from Crystals First at Marburg, with people from Enamine, Gerhard Klebe, and ourselves. The paper is submitted these minutes, essentially. Here's the idea. So that's an X-ray structure that we see here. And to make sure that we have a stable X-ray structure, first thing that we do is quickly redock that very fragment to see whether it stays where they are or where it was, and whether we can accurately score it. That said, we can now do what I detailed out before. We can grow from a certain vector, exploit the chemical space descriptions that are reaction-driven, as on the slides before, and come up with results. So here's that story. We yielded a best binder with 744 nanomolar inhibition here that exhibits 4 rings, 2 stereocenters, and the results also encompassed that we had almost 70 compounds that exhibited a Ki value of 500 or better. 6 X-rays could be obtained very swiftly. So in total, only 9 weeks were needed to go from this scenario to that scenario here. And we didn't only work on this one fragment here, but we exploited more, 4 to be exact. Here is what we did. We picked the stable X-ray, and then we did something decisive. We did a fuzzy matching, which means that instead of only focusing on this exact template here, we also allowed that other rings, for example, could be placed onto this thing. And the minimum number of atoms in a ring that we required to match is 5. So that means that on this ring here, we could just as well have fit a parallel ring or something similar like this. So this kind of broadens the spectrum that we looked at, gives us more choices to also be surprised by something which is close to the fragment, but not exactly the fragment. We did this with the FlexX anchor and grow mechanism that has been improved over all the years that it existed. We then scored using height, selected the respective compounds, completed the applicable chemical space using the reaction compatibility matrix that I detailed further a little earlier. And then we repeated the sequence with the next attached fragment, scored, clustered, filtered, triaged, visually inspected, and sent over to Enamine for synthesis. Again, the paper is being submitted, but what I would like to point your attention to is that usually what we see is a funnel. Yeah? It's like big at the top and small at the bottom. But Ceci n'est pas un funnel in this case. So this shape is a little bit different. It blows up in that range here where we do exactly that template-based docking, scoring, filtering, iteration. So in this sense, we kind of allow a breathing into chemical space while we dock and come out with those hits here at the very end. So only at the end, it comes down to the classical tunnel after visual inspection, synthesis, solubility issues that may occur, and the assays. Again, using this technology, we can have any member of the chemical space emerge as a hit. So there is no pre-triaging, pre-filtering or something like this, because we employ any building block, or in this case, our fragments that are seeds. So these were my 2-3 slides on docking. The current situation. Again, Paul Barossa tomorrow. Go and watch the talk for a longer application story of the mechanisms behind. Rescaffolding and linking is something that enjoys a lot of popularity here, and you may be aware of our ReCore functionality in SeeSAR's Inspirator, where you essentially say snip, snap, and replace something for me in there. Now, recently, Peter Ertl from Novartis in Switzerland came up with his magic idea, namely to find in drugs and drug-like compounds those rings that occur and that can be chopped out or carved out of compounds. And he wrote this up in this JSIM publication here, actually also part of the special issue that I mentioned earlier. And thankfully, Peter put up a navigation page here where you can actually, on the fly, surf through these magic rings here. It's a bit.ly shortcutted URL, bit.ly/magic rings. If you'd like to go there and take a look. It's a wonderfully written little web page here that allows you to navigate through the ring space that Peter has assembled. But we now converted these rings into a searchable 3D fragment set. So the input is the smiles that can be freely obtained from Peter's website, roughly 40K. And we used our conformator engine that converts 0D or no D into 3D. And we used a maximum of 2 conformations per entry in the smiles database, your smiles library here. To not explode too much at the end, we yielded 60K mod 2 entries here at this point, and then comes the shredding step. At this point in time, I specified that we only use the scaffolds as such. My thinking is, depending a little bit also on your feedback, or on feedback that we receive from you guys, is that we perhaps also add a joint, like a methylene group or something like this, so that if a ring doesn't fit perfectly, perhaps it would fit in a little smaller variant, but with 2 methylenes attached, for example. So here's part of the long list of cleavage and filter rules. Essentially, you see the filter gets a name, a smarts expression. Whenever you encounter any carbon that carries a hydrogen, chop the hydrogen off and leave the rest there. Give it a name, R1, so that we can denote later what has happened and what rule has applied. What this yields is something like this. So fragments where you make sure that, for example, geminal substitutions or geminal carve-outs that don't make any sense, that these are avoided, so you can impose a certain distance threshold that must be overridden in order to form a fragment, which is here depicted in red. Also taken care of is symmetry artifacts. So if you carved out, for example, something like this and something like this, so kind of opposite on each other, and this were symmetric, then this is also taken care of automatically. So this procedure in the end yielded 15 million 3D possibilities to be inserted into your problem at hand. We put this online just now, so if you would like to take a look at this, be careful. It's, I think, 6 gigabytes in size. If you download this, it will unfold into a directory and follow the respective guidelines for installing SeeSAR, Inspirator, fragment files, and please give us feedback. That's kind of experimental, so I'm very keen on hearing how this works out. But in the sense of another choice is better than no choice, I thought, why not just put it online and have you guys tested it when I talk about this. Peter will also speak. We are very thankful that Peter Ertl is on board for this Workspace event today and tomorrow. He's going to speak tomorrow at 6 p. UK time, so London 1800, and Central European summertime 7 p.m. and 1 p.m. Boston Daylight Time, Eastern Daylight Time. So if you actually do snip, snap, and insert something, then it will look like this. So the anamnesis is stored. Here, for example, there is a mouse over. We can use a magic ring denotifier 39121, for example. And actually, the target annotation is also there. It's kind of a cause target annotation that Peter has supplied here. So it will read GPCR, so you know that this scaffold has already been observed in a GPCR-related molecule before. And you can see how nicely it actually fits on these things. And actually, I can profit from the just recently implemented interactive PowerPoint 3D model export in SeeSAR. So if I now click, then we can actually visualize this in 3D. And you see this bond here is almost exactly matched in this little example. And this bond has a very small deviation. So it seems like it should be fairly good to use, fairly easy to use, and hopefully you find profit in what we have supplied on the website. Part B is we cooperated again with the CCDC. Big thanks to Carmen Nietzsche and David Bardwell, who supplied us with assistance in setting up a new ReCore index based on the CCDC's CSD database. Maybe a tongue breaker if you pronounce that too quickly. Selected from the CSD, almost 300,000, used for indexing 150,000. So of course this is owed to 3D duplicate removal and things like close symmetry artifacts, etc., etc. So even given this figure here, you wouldn't believe it perhaps. We yielded almost 50 million exit vector combinatorial containing fragments that you can then insert. So that again is also a big index. We've put it online on the CCDC's webpage. You need a CSD license to actually access this index, this fragment index, to be able to work with it. But I'm sure many of you will have a license, so you are good to go. Okay, so we talked about docking, rescaffolding, and linking and merging, all these things that you can do with these index files. And next up is growing. So growing is a wonderful, nice thing here that we can talk about. We have Patrick Penner from Matthias Rarei's lab in Hamburg, who has thought a lot about these things and how to make them fast. So essentially, what we do in here and what Patrick has coded in here is, given there is a query molecule with an exit vector, there is a compound selection, there will be some shape matching in the pocket, various filters, and at the output end, we will have a pre-specified user-specifiable number of compounds that emerge. So the trick is in the shape matching here. And if you look at this conformer that has been sampled, then for every conformer, there will be a descriptor that looks like as if rays emerged or came out of these ligands here into various directions. You already see that there is a grid-like nature, and we do just the same on the pocket side. And we then yield with this descriptor that is made to do a quick matching here between the conformer that we have on the one hand side and the pocket that we have on the other hand side. We yield an enormous speed. We can screen now 12,000 fragments in roughly 10 seconds, and this uses a bit shifting in the memory, what makes it so fast. So classically, you would use a vector and you would rotate a vector, for example, to explore a fragment in a pocket using a rotation matrix that you, I should have made a matrix symbol here instead of such a vectorial symbol, a matrix that you operate on a set of vectors here. So this makes it much, much faster than you did if you did classical rotation matrix multiplication. We are very grateful that Servier in Paris accompanied the project throughout the last years. And I again would like to thank and notify you that Patrick Penner did the brainwork behind this. He is a member of Matthias Rarei's group in Hamburg. The manuscript is being submitted, but look how it goes. Oh yeah, by the way, Jeremy Edmonds has had a very early access to this, and Jerry Edmonds from AbbVie will speak later today at 6:40 p.m. UK, 7:40 Berlin time, and 1:40 p.m. Boston time. Take a look. So I haven't seen the talk myself yet, so I'm super curious what AbbVie and Jeremy have done with FastGrow in this. But look how it goes. Here's a little movie that I prepared with a simple, relatively straight ligand that I pulled out from the literature from Nicolas Villon in Lille in France. I think it serves as a great example to exemplify what actually is going on. So you say, instead of snip snap, you just say snip, and you specify that one bond should be cut either in this direction or in this direction, which is now in my example the case. All you need to do is press the grow button, and with a click, and this is running in real time now, with a click we scan 12,000 fragments and their conformations and place them in the pocket. There they are. You can check all those that you would like to score, so this query shouldn't be scored. And then we can run over our height-based desolvation-aware affinity estimations, which also run in parallel, of course, so that's pretty speedy. And then only after a few seconds, you have not only grown, but you also have scored with a sophisticated scoring function and received an estimated affinity range. And look how closely they follow the original ligand in the pocket here. So I'm really looking much forward to having this tool in your hands. It's going to be published probably next week, and we have already progressed quite far. Next up is the similarity area. So this is an area or a part of our Armory that doesn't necessarily rely on 3D coordinates. Between similarity and similarity, there may be differences. Namely, one, for example, is a close-by Tanimoto-like similarity that many of you are used to. So I compare this here with this fisher having a net at hand to fish that is close by, as opposed to him throwing a net further away with respect to the distant and not so obvious similarities that we may be interested in. So here's an example. For example, riduzole, a channel inhibitor. It acts as a neuroprotective and has this simple build up here, benzoyl, thiazole, amine group. And if we looked at this and we said the close by, the Tanimoto-like neighbors, could be these, for example. You exchange an oxygen for a sulfur, oxazoles. Perhaps you put in a nitrogen, you let the nitrogen walk. So you have those close by classical near neighbors that Tanimoto-based methods, Tanimoto in quotation marks because it's not exactly the descriptor underneath, but the classical fingerprint methods that you have that these should pick out. On the other hand side, you have those distant and not so obvious molecules that other descriptors need to fish out, or that you would wish that other descriptors would be able to fish out. For example, this thing here, lamotrigine. It acts as an anticonvulsant. It's a mood stabilizer also, at least that's currently being investigated here. Again, we have a channel inhibitor and infiniSee and feature tree similarities that I will get you introduced or recap, do a little recap on in a few minutes. They come up with a similarity of 0.86, so comparably high as opposed to methods that would be based on fingerprint methods and that we would classically use here. So that's the distant similarity. How does that work? Well, just to remind you, many of you will have heard this before, but we describe the molecules as trees. We call them feature trees, an invention by Matthias Rahe from even before 2000. And this feature tree stores in its blobs here the information about physical-chemical properties of the contributing atoms and rings and so on. Rings collapse to blobs to one node, so this collapses here and this collapses here, so that's better visualized here. So you can see this terminal groups collapse here if they are single atoms, or single atoms that are terminal, they will collapse into the rings that they are bonded to, or into the atoms that are bonded to, which is why you see this. This is actually a halogene here that collapses into the ring, which is why you see only one blob here. Even though I depicted this for didactic reasons in a 3D way, the feature tree itself does not contain any coordinate information about the atomic coordinates, but it does contain some kind of information about the size of the contributing atoms. So the feature tree describes a molecule, and what we can then do is we can use this also when we query a chemical space, a fragment-based chemical space. So we take our query molecule represented as a feature tree, and we chop this up into pieces, and then ask the chemical space what, for example, is most similar to this part of my query molecule, and perhaps you pop out one like this, where there is a blue blob that is a little smaller, the green blob is a little smaller, but that one is a little larger. And then you have this linker information that, again, exploits this, the chemistry behind in the compatibility matrix, so that this linker knows what it can connect to, and it does that, for example, pulling out such a fragment and then continue pulling out such a fragment until we arrive at the end. All this is swiftly and very easily doable in the infiniSee software, which is displayed here with infiniSee 4. We actually are now going to display to you the synthons that are behind such a result molecule here. And you may know already the visualization where we color code what is matching on what, so that you can understand and relate to the computational result and perhaps even overwrite it with your eyeballing. Alongside the reagent or synthon display, we have implemented the analyzer functionality, which you may know from SeeSAR, where you can impose filters, triage, search for things, remember things, put little post-its to it, etc. This you can also already do here. And we have packaged a bunch of new chemical spaces in here. Very recently updated the Wuxi galaxy space, which has one almost 5-fold size increase. It now includes more complex molecules also, and we can already see light at the horizon surpassing the 10 to the 10th barrier here when the building block availability is back to normal. You may know that also Shanghai has been, and partly still are, as far as I know, in heavy lockdown, so that not everything is back to normal yet. Updated enamine real space, 29 billion molecules here. Enamine are back to normal, they tweeted yesterday. So I would like to raise your awareness that that this is looking good despite the terrible war going on in the country. Ottawa's Cambria, they operate in a very distributed way, contributes with 1.2 times 10 to the 10th. And here's the freedom space. So focus on accessibility during war times. Either you can have the full molecule synthesized from this freedom space, or simply order the building blocks and synthesize the rest yourselves. Of course, this is much smaller, but it has a strong focus on getting the molecules to your bench. Knowledge space, you can download this from our website. It's also included in infiniSee 4, has a strong focus on the size, so 10 to the 14th, a giant, vast chemical space. That said, with almost 50 billion purchasables, as I call them from time to time, you would have a great reservoir, a huge chemical space to mine your molecules from. So that was Similarity. The Tanimoto Similarity, seeing that time is progressing, was planned to only have one slide, because you saw that slide and slide modification already last year. I just wanted to let you know this is currently being ported into infiniSee, so you should be ready to exploit it also in the not so far future. The original reference to the paper is here, but since these calls, these meetings are recorded, you can also certainly look this up later in the recording. So finally, and Xabi has already mentioned this, SpaceMax, one of my favorite tools currently in our armory of chemical space search technologies by Robert Schmidt. And we are super glad that we have managed to hire Robert as a BioSolveIT employee now these days. It is super fast. It will also be accessible from within infiniSee. Currently, it's command line only. It supports various modes and these smarts expressions. So take a look here. For example, if we pop up our smarts editor and write up or sketch up a smarts query that we can then subsequently use, then essentially all we need to do is call SpaceMax in the continuous mode. That's what the -C is, and specify a file. Yeah.
You have 5 minutes left.
Yeah, thanks very much. I'm almost at the end now. And within only a few milliseconds, literally here in this example, we have the next query ready to be fired in. And the output is still smiled, and you can just copy and paste it or write this out to a file as you like. Okay, everybody today. So with this, I'm closing the armory, and we can quickly have a look at how far did we count here. So I'm breaking this down now, 3, 6, so 600 million, that's what we arrived at. So between 10 to the 8th, maybe tackling 10 to the 9th with a mere enumeration in the computer, only counting. Well, with this, I thank you very much for listening, for using our tools, for giving us feedback. It's extremely helpful if we receive feedback, be it bad or be it good. And here you can again see the surge in chemical spaces and the BioSolveIT land of chemical spaces. Thank you so much, Alex.